Okay, Chapter 8, Day 2. We talked about least squares regression lines. We talked about residuals last video and last class. What we're going to look at today is a residual plot, which is basically a plot of the residuals. We're going to take a look at some of the things that the least squares regression line can tell us, as well as what this residual plot tells us. Okay? A residual plot, what it'll do is it'll tell us if the linear model is appropriate. And the big word here that you have to realize is appropriate. It's going to help decide whether this should be modeled by linear or by something else. So what do? We make a residual plot, which is a plot of the residuals. It is the x variable along the x-axis, but the residual values along the y. All right? The calculator will plot these. If it looks like this, all right? If the residual plot shows a random scatter of points, some sort of just random scatter of points, then it will tell us that the linear model is appropriate. All right? Second residual plot. Notice this one has some sort of curved pattern to it, whether it's right side up, upside down, some sort of curved pattern. Again, we're plotting the x variable and the residuals. If the residual plot has a curved pattern, then the linear model is not appropriate. This will not tell us what kind of model is appropriate. It just says, hey, the linear model is not appropriate. All right? If the residual plot shows a fan-like pattern, so it seems to be this random scatter, but it fans out or fans in. Again, these are the resids. It says it indicates a change in variability of the data as the x variable changes. So not that it's not linear, but it's the variability of the data is changing. And so be careful using the linear model here. Maybe the linear model only is good for in here, or only for certain regions. But this shows that the variability of the data is changing as x is changing. And so that's a be careful. You want to make sure that you note that when you're using that model. To make a residual plot on your calculator, you put your data into list 1 and list 2. You run stat calc 8 like we did before, getting a linear model. But here's the thing. Hit second y equals. So now let's make a graph. Set the x list to list 1. Set the y list to resid. What happens is when you run stat calc 8, you never knew this, but in the background, your calculator calculates all those residuals and creates a list called resid. So if you just turn your calculator on brand new, you would never see the list here. But once you run this, it's here. Now, with that being said, if I give you new data, you have to do this every time before you run the residual plot. Now, that word resid you can get from second stat, because that's where the lists are. And then you look for the one that says resid. All right? Zoom 9 will zoom it for statistics, and bam, it makes a plot. I've made a resid plot here of our arm data versus our height. Okay? And notice, looks kind of like a random scatter to me. Since the resid plot shows a random scatter, the linear model is appropriate. And that's all we're saying right now. The model's not going to be perfect, but the model is appropriate to use. All right? So that's what a residual plot tells us. This is how we use it to see whether or not the linear model is appropriate. So we're going to practice making residual plots in class. The other two pieces I want to talk about is the slope. One of the things that you're going to be asked to do, and in real life we should be asked to do this, and we should know how to do this, is interpreting the slope in the context of the problem. So using the context of the problem, you state what the y variable is doing, whether it's increasing or decreasing. For every 1 unit increase, and again this is standard, in the x variable. Okay, so for every 1 unit increase in the x variable. All right, so let's say you take our arm and height data. I took some arm and height data and I have an equation. All right, So if I want to interpret the slope, you remember the slope is next to the x, so there's my slope. All right? Now, for our arm and height data, you could write it like this, or you might see the book write problems like this, where the y variable is the height, so height hat, and then instead of x, they write arm. Both of them are equally is useful. But there's our data, okay? So if I were to interpret this slope in context, well, for every one, what do we measure arms in? Centimeters? For every 1 centimeter increase in someone's arm length, the y variable, height, increases by 3.95 centimeters, okay? The x variable, we're always going to talk about a 1 unit increase. The y variable, again, increase or decrease, it depends on whether the slope is positive or negative. For every 1 centimeter increase in our arm, our height will increase by 3.95 centimeters. That's the slope in the context. The other one that we talk about is y-intercept in context. And when appropriate or when it seems that it fits for what we're talking about, it's not always useful. So when useful, I should say, maybe instead of appropriate, you state what the starting point is when the x variable has a value of 0. Okay, so let's take a look at our equation. Our x variable has a value of 0. So our arm has a value of 0. If I put a 0 in here, here's our starting point, okay, for height. So let's see how silly this sounds. Okay? For a person with no arms, the height would be 32.4 centimeters. Again, probably not too useful to us right now or not too appropriate. Other times it is useful and appropriate. But when you state the y-intercept in context, you talk about, for whatever situation you're working with, when that has a value of 0, what is the y variable going to be? And there's times when it's appropriate to use it and times when not. And we're going to work on problems now in which we have to state the slope and y-intercept in context as well. And that's it.